Hi there, I'm Professor Patrick Degener. This is Bioelectronics, and in this lecture I'm going to cover the first stage in the Cellular Bioelectronics section of the course. What I want to try to do is to review the concept of charge and how it flows through materials, especially biological materials, which is a little bit different. And then we're going to discuss diffusion processes, drift processes, and how they come together in systems such as p-n junctions, galvanic cells, and electrolytic cells. And then finally, I will discuss briefly about what this means in terms of cellular bioelectronics. How do cells take charge in and shift charge out of their cell membranes? So, first things first is, charge. What is it? So classically, we think of a system described here, where you have some block of material, you put an electric field, a voltage across it, and charge follows the electric field. Positive charge follows the electric field, not electrons. Electrons are the opposite direction. Yeah, sorry, it can be a bit confusing. But positive charge follows the electric field from a positive domain towards a negative domain or a ground, typically. So, and if this moves through a resistive material, you need a voltage to push it through. So normally define current as the movement of charge with time, dq dt. Or how many coulombs per second is shifting through your material. And this forms, and a coulomb is defined here, 1.6 by 10 to the minus, a single charge is 1.6 by 10 to the minus 19 coulombs. And again, we have this Ohm's law that the voltage is equal to the current times the resistance of material. If you want to think of that in a somewhat different way, we can talk about, instead of talking about the current, we can talk about the current density. So if you imagine current moving through this material, the current density is the density in terms of the area. So the advantage there is that the current density does not change depending on whether your block is wide or your block is small. But in essence, another way to describe this current density is in terms of the conductivity times the electric field. And this is an important concept. So normally we think in Ohm's law of V equals IR, I is equal to, so if we come down to Ohm's law here, we normally think of I is equal to the V over the R. Yeah. But now we're talking effectively that this is, this current is proportional to something called conductivity times the voltage, where conductivity is a bit like 1 over the resistance. But it's a very useful term, and we'll talk about it more later on in the course. Another point to note is that we have this common equation to expand out what we mean by drift current. So drift current is where charge is being moved due to an electric field across it, and the drift current is basically due to the number of charges, charge and electron, how easy it is to move through the material, the mobility of that charge, and the electric field. So these are the basic concepts. You may have learned these before, but it's just worth revisiting these again. Now, let's think about this in a little bit more detail. So normally, as we've described before, we think of putting a voltage across a particular source, and as a result, a charge moves through this material. This is our resistor, and our resistor has a length and an area, and then the two things that we consider is that the voltage across that resistor is equal to the current times the impedance, if we think of AC, or resistance if we think of DC, or the current is the voltage divided by the resistance, if you want to shift the equation around. And then it's worth noting that the the resistance is defined by the resistivity of the material. So in here there's a resistivity, and the resistance is that resistivity multiplied by the length divided by the area. In other words, as you make a resistor longer, it becomes more resistive. As you make it wider, it becomes less resistive. This is all fairly straightforward stuff. Now, there aren't just resistors, there are capacitors. And the symbol for capacitor is two parallel lines. The reason for that is to define that current will come up to these two parallel lines but can no longer cross. There is now a gap, so DC current cannot travel through a capacitor. AC can, but DC cannot. So as a result, if you had a voltage here, and or actually let's say this is a current source. So if you have a current source here that's defining this current traveling into this capacitor, well, in the beginning there's no charge, but very, very quickly charge will build up, and you'll get positive charge on one side, negative charge on the other side, and then eventually it's no longer possible to push new charge up against these walls of the capacitor, and the current stops, and a steady state is reached. When that happens, we can say that there's now a voltage across these plates of the capacitor, whereby the voltage is determined by the charge across the two sides and the capacitance of the capacitor. So if you have a larger capacitor, the same amount of charge gives you a lower voltage, and vice versa. And we can define the capacitance in terms of the permittivity. So E or epsilon naught is the fundamental permittivity in free space. Epsilon r is the permittivity of the material in that gap between those plates, and then of course there's the area and the distance between those two plates. So here we've got two different scenarios. One is where charge is moving through a resistive material, think of walking through treacle, and the other is where charge has been stuck up against two plates. So this is where, imagine walking down the street and suddenly seeing a wall in front of you, you can no longer get through. So these are the two scenarios for traversal. But in either case, there's a relationship between that movement of charge and the voltage, which is the electric field. Now, I think it's important to think about what is charge. So normally we think of electrons. Electrons float around atoms, or and these come together in ions and in sort of metals and in compounds. And if there is a free electron that can move around that material, such as in metals, then charge can traverse very easily. In the case of semiconductors, it's a little bit harder, and in the case of insulators, it's really challenging. There's no free charges which can move around. However, it's not that simple. So normally in metals we think of electrons movement, but in semiconductors we also have this concept of holes, which is a bit of a strange concept if you haven't come across it before. Conceptually, you can think of a hole as where an electron shifts from the valence band up to the conduction band and leaves this gap, this hole behind it. It's much better to think of holes as actually independent particles rather than the absence of an electron. And once you think of it as an independent particle, it has a mass and it's got spin and it's got all these other properties which you can measure, and it's better to think of electrons coming in one way and holes coming in the other way. Now, it's also worth noting that there are other ways of considering charge. So in organic semiconductors, where effectively you've got these single bond, double bond, single bond, double bond type scenarios, where you've got a kind of a bond defect, we can think of negative and positive charges as a kind of a bond defect. These are called polarons, but again, in the same way that you can think of holes as the absence of an electron in a semiconductor, but actually it's easier to think of it as an independent particle. In the same way, for these kinds of materials, it's still easier to think of these in terms of two particles, electrons and holes. Electrons are negatively charged, holes are positively charged. And then the final aspect to point out are electrolytes. So in essence, electrolytes are salty waters, and our table salt that we use for our food typically consists of sodium chloride and also potassium chlorides and a whole bunch of other things. Sodium chloride is the most important one. But in essence, once they go into the solution, that strong bonding between the sodium and the chlorine starts to become a little less strong, and they kind of float around with a certain affinity to each other. So we think about positive sodium ions and negative chlorine ions. So these are no longer strange particles called electrons and holes that somehow move through the material, but rather it's the material itself which is moving. It's the ions, the actual metals, or the non-metals that bond to it. Now, the first concept I want to try to bring forward in order to we've talked about drift currents, which is charge moving under the influence of an electric field, but there's also this other concept called diffusion. So if we take a scenario where you've got a box, there's a bar in the middle of that box, and in one side there's a high concentration, in the other side there's a low concentration. Now, if that bar is permeable, well, over time, then the atoms start to move around until there's roughly an even number of atoms on either side. This is called osmosis. Now, an interesting aspect is if you set up your system such that the water can move, but the ions, the heavy salt particles cannot move through a membrane, then you get this kind of scenario where in the beginning you've got a low concentration on one side, you've got a high concentration of salt on the other side. If the ions can no longer move, well, then the water moves, and you get this kind of scenario here where you now have you've now got a low volume on one side and a high volume on the other, such that the concentration is the same on both sides, even if the volume's not the same. So what's happened here is that you've had a movement in order to get an equilibrium, an even concentration on both sides of that membrane. Now, the person that developed the concepts around diffusion was Albert Fick, and he developed what's known as the Fick's law, which is this diffusion law, which is a very simple law, which says that the current, the movement of these charges or these components, could be gas, is related to the diffusion constant times this first order differential equation, which relates to the concentration gradient. And to cut a long story short, but if you integrate this, you always end up with an exponential function, which is quite important. Now, in order to define the diffusion constant, what is that thing? Well, there was a little bit of an interesting discussion between Albert Einstein and Smoluchowski, and it's now known as the Einstein well, actually, it's just the Einstein law. Smoluchowski got knocked out of history, unfortunately. But it is actually the Einstein-Smoluchowski relationship. And that defines the diffusion constant in terms of how easy it is for the charge to move, or the component to move, the mobility, the Boltzmann's constant, and the temperature. In other words, higher temperature makes it easier for things to move around. And I mean, it should be noted that sometimes it's given in terms of this, which is RT, which is the gas law. For us in the electronics field, as opposed to the chemistry field, we like the equation in this form, with mu being the mobility of charge, rather than thinking about gas constants per se. Now, where this matters, I mentioned briefly in one of my previous lectures about the this concept of the diode that was, the equations were developed by Shockley. And in a diode, what you do is you put a p-type semiconductor and an n-type semiconductor together. They're in equilibrium by themselves, but when you put them together, there's an excess of p-type charges on one side and n-type charges on the other, and this results in movement of charge through what are called diffusion processes. Now, as you move charges from one side to the other and vice versa, this now causes excess charge to build up, and this creates an electric field, and the electric field causes a drift current in the opposite direction, until there is then an equilibrium. And then if you want to pass current through this in the forward direction, you utilize the Shockley equation that we described before. So those of you that have studied semiconductor devices before will have seen this particular equation. But the same concept doesn't just exist in semiconductors. The same concepts also exist in salty waters and salines. So let me describe first of all the galvanic cell, which basically is a battery. So two solutions, a zinc sulfate and a copper sulfate. Let's put an anode and a cathode in, zinc and copper respectively. And what you'll get on one side, once you put your electrode in place, there'll be some interaction with the solution, where the zinc can now become, an electron can be taken up, and you can start creating new zinc ions into your solution. Similarly, on the other side, you can get a reduction of copper, and what can happen is that your zinc can traverse across, take up the, steal some copper sulfate, and then the copper can be taken up by the cathode. And if you were to put an electrode across this, you would actually see a voltage. And that voltage is the sum of the oxidation and the reduction potentials of these two chemical reactions. So what we see here, this is the basis of batteries. But what we see here is that, movements of charges through diffusion processes, because there's more zinc in the anodes than in the solution, zinc starts to move into solution and then traverses across and gets taken up by the copper. This is a kind of a permeable membrane. This black bit here, this is a membrane that allows ions to get across, but not the solutions. And then you start to see a movement eventually. The copper electrode builds up, the zinc electrode decays, but for a while you get a voltage and you get currents. Now, we can do the opposite, where let's say we take some saline, and in this stage, let's say we put two electrodes on either side, and then we put a voltage across the two electrodes, and the voltage will create a current. So this is drift. So drift current is where you make an electric field, and this electric field forces charge to move in particular direction. The charge goes into the electrodes and you get oxidation reactions on one side and reduction reactions on the other side. And then what happens is what happens is you get movements of ions from one side to the other, which effectively is a drift process, and this completes your current. So that's all fine, but if you get too much, if the current is too high or the voltage is too high, you can start getting gas formation on either side, which, you know, if you were to do this inside a human, this would not be a good idea, because the gas bubbles would block up our blood vessels and potentially hurt our heart. Divers will know this as the bends. So the concept here is that you can put metals into separate solutions and you can create batteries, and, you know, through movements of charges through the solution, you can generate voltages and you can generate currents, and vice versa. If you take a battery or some kind of voltage source and you force current through electrodes, you can force the movement of charge through a solution. So the important concept here that I want you to take away is that we shouldn't think of current and voltage as something related to electrons moving through metals. That's true, but it can also be related to charges moving through salty waters. So in the next lecture, what I hope to do is to explain what this means in terms of cells. But as a spoiler alert, if we think of a cell as this kind of membrane that I'm now highlighting, cells effectively have leakages and sort of methods such as ion channels for charges to leak inside, and then they've got structures which pump charges one way or the other. And if you pump out negative charges from inside the cell to outside the cell, then eventually you end up with a charge, yeah, or let's say you end up with less charge compared to the charge concentration in the negative, or sorry, in the positive compared to outside, and this makes your inside a little bit more negative, and that creates a voltage, across your capacitance, which is your cell membrane. So if you remember at the start, I talked about capacitances, and charge across a capacitance creates a voltage, and exactly the same thing happens with cells. And there's movements in and out of cells due to these ions such as chlorine, potassium and sodium, and to a lesser extent calcium, that move in and out. And where is this important? Well, on this course I'm going to have a big focus on especially the nervous system. It's my personal interest, but this is really important for your muscles. You know, if these movements of charges in and out of your muscles don't happen, your muscles don't work. But also even bacteria. There's lots of bacteria out there that have to be constantly, for example, purple bacteria live in really salty waters and they have to be constantly pumping out the salt in order to perform their normal functions. So there are lots of different interesting aspects in this across the across the world. So thank you very much for listening, and see you at the next lecture.